Okay, and thus the topic we are going to start today deals, as I anticipated to you last time, let me say, with another class of specialty materials, of non-conventional materials, which do show specific and controlled electromagnetic properties. And so we can enter the field of the so-called RAM, radar absorbing materials, and radon materials. This second term is a composition of radar by suppressing DAR plus dome, and it indicates as a component a dome-like shell, which is not absorbing, like in the radar absorbing area, electromagnetic energy, but which is transparent to a selected radio frequency radiation, and which is usually used to house a radar antenna, for example, for guidance system. As you can understand, many of the information in this area, they are sensible information, not available, let me say, not publicly available, but we can say something, and we can give to you some basic concept in order to understand which are the main design criteria which must be followed in order to achieve the goal of fabricating an RAM material or a radon material. Before entering in our field, this the field of materials, we need to make some general remind for all of you in order to better understand what we will say later on. And a reminder which is related to, generally speaking, the interaction between an electromagnetic wave and a solid materials. So we are dealing with the electromagnetic spectrum, which I can remember to you can be divided or can be sequenced according to frequency, or they are not independent, as you can remember, according to wavelength of the electromagnetic radiation. And so we have different fields, which also suggest fields of application. So we have the area of the visible light with all the colors, which are differentiated according to the wavelength and thus according to the frequency. We have the area, for example, of the ultraviolet, of the X-rays, the gamma rays, the infrared, radio TV, the long waves, and the area of the microwaves. The area of the microwaves is thus interesting for us for our discussion. It covers more or less the range of frequency from 1 to 1,000 gigahertz as whole field, but most operation radar are placed inside the range from 1 to 40 gigahertz. That is inside the microwaves range. But we do have also classification of waves and frequency ranges due to the fact that the interval, the range of the frequency, which can be associated to the whole electromagnetic spectra, is up to 10 to 24 hertz. So it's a very large and a very complete range, which is subdivided in subclasses. And there is an historical, let me say, classification or a traditional classification with a waveband name, which is partially still used in the literature, and the more recent criteria adopted, which are represented here in the following slide, according to the classical, thus the IEEE, and to the leader classification, which is those reported in blue on this slide. Obviously, there is a correspondence, and for what it concerns our interest, we can say something generally in order to place better, I would say, applications and then also response of selected materials in the area of radar, generally speaking, just putting inside both the case of the radar absorbing and the case of radon materials. So just to summarize and give to you basic elements, we can say that the C band, according to the leader classification here, which corresponds more or less to the UHF classification of IEEE, is, let me say, a band of frequency which is include between 300 megahertz and 1 gigahertz, which is considered to be a good frequency for the operation of radars for the detection and tracking of satellites and ballistic objects over a long range. The radars which work in this area, they usually have a duty that is to operate for early warning and target acquisition, like it happens in the field of surveillance radar. There is also a new technology in this area, the so-called ultra-wideband UWB radars, which is going to use all the frequency from the A to the C band. And they transmit usually very low pulses in all frequencies at the same time, that is simultaneously, and they are used for other purposes with respect to those we have just mentioned, because they are used, for example, in the area of the ground penetrating radar, the so-called GPR, for example, for archaeological exploration. The second is the D band, which corresponds to the L band radar. And this is a frequency which is more or less centered around from 1 to 2 gigahertz. And it is found in the operation of long-range air surveillance radars out of about 400 kilometers. In this case, the radar, they transmit pulses with high power, broad bandwidth, and with a specific modulation. And due to the curvature of the Earth, the achievable maximum range is limited for targets flying with low altitude, because this object will disappear very fast behind the radar horizon. In the air traffic management, ATM, long-range radars in this, as this we have defined, works in this frequency band. And then there are also some variation, because they could be pulsed, they could be coupled, sorry, with monopole secondary radars to use a relatively large but slower rotating antenna. But in any case, the designation L band is a sort of good mnemonic rhyme for large antenna or long range. The G band, which corresponds more or less to the C band radar, in this band, there are many of the mobile, not civil, let me say, applications, as in missile control, ground surveillance, set with short or medium range. In this case, we do have a very good, due to the size of antenna, accuracy and resolution, but the small size antenna, which can give these results, don't bother a fast relocation. And in this case, it has been observed that weather, and especially bad weather, has an impact which cannot be neglected. And so there are some other traits which are located into the electronic expertise, for which air surveillance radars use also an antenna field with circular polarization. And this can, let me say, reduce the drawbacks we have mentioned. And this frequency band is usually predefined for most types of weather radar used to locate precipitation, for example, in temperature zone like in Europe. Then there is the EJ band, which corresponds to X and KU band radars. And in this frequency band, from more or less 8 to 12 gigahertz, we have a relatively popular application that's a relatively popular radar band, again, for military application, like in the case of airborne radars, for performing the roles of interceptor, pilot, and attack and ground targets. Also in this case, the antenna size is quite small and provides a good performance, and it is used also for guidance system, again, for systems which are not allocated in let me say, civil application. This frequency band is widely used for military navigation radars, in some cases also for civil in the sea navigation radar. Then this is just the, let me say, background about the classification of the radar band. And as you have more or less seen in the fields, which is interesting for our topics we are going to discuss, we are in the range, as I told to you, from 1 to maximum 40 gigahertz, from 1 to some tens of gigahertz, we could say. So let's move a little bit now on the material side. And material side considered as responding to electromagnetic radiation or electromagnetic waves. On the basis of their macroscopic behavior, I mean materials behavior in this case, they can be classified looking to some specific properties which are not structural properties, but are properties which can describe the interaction with the electromagnetic wave as dielectric materials. And in this case, we can have dielectric with loss, energy loss, or without loss, as, let me say, conductors, perfect conductors or good conductors, as semiconductors, or as materials having magnetic response, again, as in the dielectric case, with loss or without loss, apart some special combinations, materials with free fillets, which can combine, let me say, materials having different properties. Also in this case, as it happens, even though now we are talking about different topics, but as it happens when we have frequently discussed about macroscopic mechanical properties, for example, of materials, we can have linear or nonlinear medium. That means materials which respond linearly or non-linearly. We can have the concept of isotropy or anisotropy, and we can have the concept of homogeneous behavior or heterogeneous behaviors. And the meaning, even though now they are referred to electromagnetic properties, is just the same of those we have discussed when we have talked about, for example, mechanical properties. Remember the relationship between an applied stress and a corresponding deformation, which can be linear or nonlinear. Remember the fact that when we talk about general properties, for example, strength of the material, we can have an isotropic behavior, that is, the strength is the same in all directions, or non-isotropic behavior. So we have a differentiation which requests to us the use of a specific, let me say, system, which is given by the Miller-Bravais indexes. Or we can have, again, to see, for example, change properties, Young modulus, an homogeneous or non-homogeneous behavior of the materials, that is a value of the Young modulus, which is the same in each point of the materials, or which is, for example, due to changing chemical composition, different from point to point. So this, just to say that also the properties which characterize the electromagnetic response, that is the interaction of a solid material with an electromagnetic wave, is described by looking to specific material properties, which will be not the strength, will be not, let me say, the yielding strength of the materials, or the tensile strength of the materials, or the fracture toughness, but which will be other, that we will remind in a little bit, for which we need to be sure, or we need to define the possibility to have a linear response, the possibility to have materials with isotropic or no properties, or homogeneous or no properties. And let's go a little bit inside to some of these properties which are important for the electromagnetic behavior, and which will be then found also, let me say, as selecting or design, if you want, parameters for material selection due to the application we have in mind. And let's start, just to make this remind, whereas with a very simple case, discussing about, for example, dielectric properties. And the simple case is the case of a plain capacitor, plain condenser. We can remember that if we put inside the conductive plates a dielectric material, the capacity of the capacitor increases. And this happens because the dielectric materials is able to be polarized. And the capacitor, the capacity increases to a value which is given by a very simple formula. C, which is the capacitor, capacity, is given by the ratio between the permittivity epsilon of the dielectric, in this case, the surface of the flat phases of the condenser itself, and the distance, that is the thickness of the dielectric materials, which is put inside the capacitor. So the equation is very simple. And we here have the permittivity of the dielectric, which is a property of the dielectric itself. Generally, to be a little bit more precise, when we talk about this, we refer to the relative permittivity, which is also called dielectric constants and which is named epsilon r with the letter R added. And this relative permittivity, epsilon r, is given by the ratio between the permittivity of the materials itself, epsilon, and the permittivity, epsilon 0, which is given for vacuum, which is more or less the same for air, that is equal to 1, as it happens in most cases in which we are thinking to gases. And so, having defined the relative permittivity, we can also write the same formula of the capacity of the condenser as it is written here, C, equal to the relative permittivity, which multiplies the vacuum permittivity, epsilon con 0, which again multiplies the ratio between the area of the flat phases and the thickness, that is the distance, the thickness of the dielectric materials. Most dielectric materials have values for the relative permittivity, which is between 2 and 20, even if materials having low density, such as foams, for example, we studied polymeric-based foams, they are very near to the relative permittivity of air or gases that is approaching the value of 1. And so the capacity is just a way which we can use, for example, to measure the dielectric constant of materials. Remember that this comes, and I think this is known to you, by the fact that the capacity is given by the ratio between the charges Q and the voltage V, because the charge which is stored in a capacitor is measured by integrating the current that circulates as a potential difference V applied is going to be increased. Then this concept of the permittivity is not only used when we have continuous current intensity, but it is used as other, let me say, properties of materials in this area when we are going to overimpose, for example, a potential difference with V, which is varying with time by a sine or a cosine way. That is in presence of oscillating charges. And in this case, remember that we can define for the permittivity a real part of the permittivity and a complex part of the permittivity, which are defined as epsilon 1 and epsilon 1 minus the imaginary I multiplied for epsilon 2, and which is something again related to materials property. Another important concept that we must remember, because it's important for our discussion and which is related to the fact that the dielectric materials can be subjected, as I told to you in a moment ago, to oscillating field conditions, that is oscillating potential, for example, is the so-called loss tangent and the consequent loss factor. It happens that the polarization due to the applied voltage is able to cause a small displacement of the charges, and this is both electronic and ionic, of the molecules, and this displacement of charges is something similar to an electric current. And in real dielectric materials, this current dissipates energy, just like a current which is going to be circulated in a resistor. And this results in a phase shift between the applied voltage and the resulting current intensity. If we define delta, the angle which is able to characterize this observed phase shift, then we can define the loss tangent like the tangent of the shift delta. And this is called also dissipation factor D, and is important because the power factor, which is defined as PF, is the sine of the loss angle. And so it is going to be applied the equation PF equal to D, more or less, for small shift, this works well, equal to the tangent of the shift delta, and due to the definition of the trigonometric definition of the function tangent, this is equal to the sine of the same phase shift delta, when we have small phase shift that is more or less the cosine of the phase shift delta is approaching 1. And in the case, as in this case, of oscillating field condition, we can define the tangent of the phase shift delta with reference to the dielectric properties of the materials. You see here, real and imaginary part of the dielectric constant, together with the frequency, that is the pulsation of the wave, obviously, they are related, and the electrical conductivity of the medium. Why this loss tangent, and then, as we will see in a moment, the loss factor is important? Is important because we can define, according to what we have said, the loss factor as the quantity which is obtained just by multiplying the loss tangent, and that is the tangent of the phase shift delta, by the dielectric constant, which we have defined before, epsilon r. That is the relative permittivity of the dielectric materials. And this quantity, L, which is the definition of the loss factor, just gives to us a measure of the energy which is dissipated by dielectric materials in oscillating field conditions. That is, its power loss. And so if we have in mind to select a materials which has as, let me say, as role or as duty, the minimization or the maximization of the dielectric losses, we can use this quantity L. That is, we have to minimize L if we want to minimize the dielectric losses, and we have to maximize L if we want to maximize the dielectric losses. And thus, if we put together what we have seen in the previous slide and what we are going to discuss now, and we are going to think now to a dielectric materials which is working in a cyclic electric field, having, for simplicity, a fixed value of the amplitude, which we call E, at a fixed frequency, which we call F, the power, in the case of oscillating condition, P, which is dissipated with a consequent attenuation reduction of the field per unit volume, is given by the product of the frequency, the amplitude to the square, thus elevated at the exponent 2 of the electric field, the value of the permittivity of the void or air, epsilon 0, and the loss factor, L. And so higher is the frequency of the field strength, higher or greater is the loss factor, higher is the relative permittivity, higher is the tangent of the phase shift delta, higher or greater is the energy dissipated, which is usually dissipated in heat. And dielectric losses is not a concept used only in the area we are going to discuss, but just to give you another example, this effect has been used, and we will make also another example, which is outside our field, is used for some welding techniques, for example, for polymers, based on a radio frequency approach. Obviously, we need to think, in this case, to polymers which are able to show a melting point that is not thermoset materials, but thermoplastic materials. So in this case, when we want to use this dissipated heat to make welding, we need obviously to put on the table all the conditions which can maximize, predefined, the dielectric losses, obviously. Here you have a table, some tables in these slides and in other slides, in which you can find quite easily, even though they are reported again on a specialized test, the dielectric constant of different materials relative to vacuum, together also with the dielectric strength, because you know there is for dielectric materials also a limit value of the applicable potential in order to avoid, as it happens, even though they are different things, in the case of piezo materials, in order to avoid breaking of the dielectric itself in terms not of physical breaking, but in terms of activation of percolation paths, which can then give rise to electrical conduction, and also the value of the loss tangent. So this table is something which is referred to polymeric-based materials, ceramic-based materials. As you see, for example, we have aluminum silicate, alumina, we have ABS, we have epoxy glasses, we have fused silica. This one is essentially related to other non-conventional materials, in which we have also, and again, ceramic materials, but also thermoplastic materials, as well as polycarbonate, as well as polystyrene, as well as PVC materials. Sorry, I go back a little bit. You see here, air is one, okay? Like in void, more or less. And this is another in which you have also, again, other values. So you have a very short database in case you need some initial reference point. What I can suggest to you is to have a look to the last column where the loss tangent is reported. Loss tangent, which is this one we have defined here, okay? what we see that this is a quantity which is not independent by the frequency. And this is another matter which is important for our discussion, because we need to deal with a range with frequencies, and this means that the dielectric properties of the materials, they do also depend on frequencies. And so we can define, for example, an optimal situation for a given frequency in terms of maximizing or reducing, in the case of oscillating fields conditions, the losses, the dielectric losses, but this can be optimum for that frequency, cannot be, let me say, suitable if we change frequency. And obviously, in our field, since we are talking about the possibility to detect a flying object, the systems are not working in a fixed frequency, with a fixed frequency value. Let's go on. Another example. So somebody of you already know, but just to remind, the dielectric losses are used outside our field in the microwave heating, because all foods that contain water, they have a high loss factor defined as we have defined before. And so we can have a very fast method by using the microwave in our house, which are absorbed uniformly through the section. And so we can have a very effective heating, which again is not usually and is not used also in our kitchen, that is for private purposes, but also for other applications, as in the case of industrial heating, for drying wood, or seasoning adhesives, or in some cases printing polymers, or some experiments have been made also in the field of sintering ceramics materials, having the possibility to reach high temperatures, which are that temperature able to activate solid state diffusion, by relying on microwave heating. And this requires the use in the sintering, let me say, step of a material having high dielectric losses, that is, high possibility to convert electromagnetic energy in heat. Also, in this case, the higher is the frequency, as we have seen before, of the applied electric field, the higher, the greater is the heating. And in common industrial microwave application, frequencies which are used are in the range of the gigahertz, something which is around 1 gigahertz, to be precise, from 0.3 to 3 gigahertz. So it is in the range of frequency, which is also interesting to our purpose. Now, can be this possibility to dissipate energy, essentially, that is to dissipate energy of an impinging electromagnetic wave used, for example, for the stealth technology, which is the subject of the radar absorbing materials. Well, the radar is an equipment which is based on the transmission of a sequence of radio frequency waves in the area, as we said, of the in the range, as we said, of the microwave. And these, let me say, waves are, if are reflected by an object on the path, that is on the direction they meet, then the radar antenna can work also as a receiver, and it can measure the time which is requested to return the reflected waves, from which it is possible to calculate the distance and also the speed of an object. And generally speaking, the metal body of an airplane is an excellent radar reflector. And also, as we will see also today in a video, which is quite nice, the curved shape of the, let me say, standard airplane let the possibility that the reflection can happen in all directions. And this is exactly what is necessary to guarantee safety, for example, in air traffic control, to identify distance and speed of the flying object. But if the goal that we have in mind is to avoid to be detected, well, this means that reflection is obviously the last thing we want. And so the area of the stealth technology is something which deals with the necessity to suppress as much as possible reflected electromagnetic waves. And this means that the impinging electromagnetic wave on the flying object must be in some way, let me say, dissipated if we refer to the energy of the electromagnetic wave at the beginning. But the topic is not, let me say, related only to the interaction between the electromagnetic wave and the material in terms of capability to suppress reflection or to maximize, for example, absorption. Because this is a topic in which many disciplines are inside, and apart from the possibility to define materials being for their properties transparent, semi-transparent, or non-transparent to microwave, materials which can absorb microwaves, also shape and size, obviously, but mainly shape of the flying object, that is the form, plays a very important role. To this purpose, looking to the shape, and we will have some other analytic definition, but now let's go into the concept. There is another important aspect which must be considered together with the electromagnetic properties of the materials itself, and which is defined for the flying object radar cross-section, written also RCS. And this radar cross-section is a sort of analytical measurement, but it is a finite numeric value of the detectability of the flying object, which is for us our target, and depends also on surface shape of the flying object itself. And thus we have to have in mind this, because our purpose is to reduce this quantity in order to reduce detectability of the target. So our purpose is to go toward solutions for which the radar cross-section of the flying object is as low as possible. And this concept integrates a large number of concepts, that is, of disciplines, starting from material science, so properties of materials, electromagnetic properties of materials, but also moving to aerodynamics, structural calculations, so something which is going to, let me say, directly affect the performance of the flying object related to the shape of the object itself. And so we can have special forms like this in the field we are discussing for the reasons we will discuss later on, I hope for you clearly. This is our reference, as we told. So we have a transmitter receiver, which is the radar. We have emitted waves. We have the target. So the interaction of the electromagnetic waves with the target can give reflected waves. And from the signal, which is detected by the receiver, we can have the measurement of the speed and the location of the, that is the distance of the flying object. So if we want to reduce detectability, we need to more or less suppress, let me say, the green wave, which is given back, we say in a correct way, which is back scattered by the flying target. Radar cross-section. Let's go a little bit inside to this concept, which is very important, to a definition level which is suitable for your interest. So we said that the radar cross-section of an object is going to describe the capacity, I call here the reflective strength, in the direction of the radar system. And it is a ratio of the backscattered power per solid angle, that is what is coming back in the direction of the receiver from the target in the direction of the receiver, that is of the radar, and is a ratio to the total power which is impinging by the target, which is intercepted by the target. It is not a geometrical cross-section of a target. And in the case, for example, of a sphere, the radar cross-section is independent of frequency if operating a very low wavelength, where the frequency is very high. Whereas in case of flat plate, the RCS is dependent on the frequency and is calculated according, for example, to the formula that it is reported here, where A, capital letter, is going to represent the area of the plate, and lambda is obviously the wavelength of the plate itself. There are also other definitions, mathematical definition of, let me say, the RCRs, like the last one, which is reported here. But this is a very important concept. Can also be defined, and this is sometimes very used, in terms of dBSM, that stands for decibel square meter, by the expression which is reported there. That is 10 multiplied by the logarithm in base 10 of the ratio sigma divided sigma r, where sigma here, they are not strength. We are not talking about stress, but sigma r is the way in which the radar cross-section is defined for a reference object having an area of 1 square meter. And so according to this equation, the radar cross-section having a value of 10 decibel square meter is 10 square meter, 20 decibel square meter is 100 square meter, and for example, minus 20 decibel per square meter is 0.01 square meter. And lower is the value of the radar cross section of the materials itself, lower is the detectability of the flying object. RCS of a target is a function of many factors. Shape is important, but this is also important frequency, aspect angle, and the dimension of the target, as well as the polarization phenomena which can occur at the surface of the flying object itself. And in order to be, let me say, perhaps a little bit more clear about the importance of this parameter sigma, okay, that now for us stands for radar cross-section, we can have a look, let me say, to the simple general equation, which is on the basis of a classical free space radar equipment, this one, where we have at the first member of the equation PR, which is the power received by the receiver, thinking now that radar is going to work as a receiver. And this is equal to PT, which is the power which is transmitted by the radar antenna. So in the case the radar is working as a transmitter, multiplied by per some quantities. G is the antenna gain, lambda here is the wavelength, P Greco is the solid angle indicating, and then we have R, which is the detection range, that is the distance to which the flying object can be detected. And here we have the radar cross-section sigma. And so if we have in mind the power which is received, okay, we can say that this equation is going to show that the detection range varies as the fourth root of the radar cross-section. And here you have some specific mathematical, let me say, numbers, figures, in which you see how reduction in dB of the radar cross-section, which correspond to this percent value, can give an effective reduction on the detection range, which is the important thing which we want to achieve, because this means that if the detection range is going to be lower, in order to detect the flying object, we should need that this flying object is more near the radar. And so, let me say, can be hidden for a bigger distance. Some examples of the RCS value you have in mind, fortunately, they are not commercial plane, but perhaps you have in mind the shape of the B-52, very rounded shape. You see here, more or less, we have an RCS value of 1,000 square meter, which makes this plane easily detectable. If we move to the first, the F-117, stealth experience of the US Air Force, well, you see here, according to the shape and size, and then also materials play their role, but the radar cross-section was going to be decreased starting from 1,000 square meter, for example, of the B-52, to 0.01 square meter. That is, it's a reduction of 10 order of magnitude, working also on the shape of the plane. To have a, let me say, a brief history on what it makes an airplane stealthy, repeating also in a graphic way some of the concepts that we have just mentioned up to now, let's have a look to this short video, which by images perhaps can contribute to clarify what we have said, what we have said up to now. So let's start, and then at the end, we will continue with our discussion.
The first major combat use of modern stealth technology occurred in 1991 when the F-117 Nighthawk was tasked with attacking heavily fortified targets in Iraq as part of Operation Desert Storm. These jets were able to sneak past the Iraqi defenses and take out important military assets, all the while going nearly undetected. Today, stealth has evolved and given us even more evasive aircraft, such as the B-2 Spirit stealth bomber, the F-22 Raptor, and now the F-35. But how did these incredible aircraft come into existence, and how exactly does the stealth technology work? Stealth technology can be traced all the way back to World War I, when the Germans experimented with the use of translucent cellulose acetate, a transparent covering material to attempt to reduce the visibility of military aircraft. However, this never ended up working out too well, and instead made sunlight reflecting off the aircraft even more visible, and the idea was ultimately scrapped. A few decades later, during World War II, the Germans took another crack at stealth technology and developed the Horten HO-229 flying wing, which became the world's first flying wing to be powered by jet engines. Ultimately, the German aircraft ran into numerous technical issues and never saw combat, but nonetheless, it was an incredible achievement for its time. As World War II came about, so with it came major advances in radar technology, and thus the demand for stealth technology as well. One notable radar system during this period was the British early warning radar system known as Chain Home. The system was built and developed by the Royal Air Force before and during the Second World War to detect and track aircraft attempting to cross the English Channel. Composed of 21 operational stations, the system allowed Britain to provide radar coverage for the entire Europe-facing side of the British Isles, as well as high-flying targets over France. This proved extremely important, especially during moments like the Battle of Britain, where the Royal Air Force was able to defeat the powerful Luftwaffe successfully. The network was even capable of providing early warning to V-2 rockets being launched within Germany. Radar, which stands for radio detection and ranging, works much the same way as if you were to shout into a well or canyon. As your voice propagates towards the bottom, an echo occurs because some amount of sound reflects off the bottom of the well. By determining the length of time between when you first shouted and when you heard your echo, you can determine based on the speed of sound exactly how deep the well is. Radar works the same way, except that it uses radio waves instead of sound waves. Whether it is mounted on a plane, ship, or it is part of a ground-based system, radars operate generally in the same fashion. A radar system will generate a short, high-intensity burst of high-frequency radio waves towards an intended target. These radio waves will then bounce off an object, such as an airplane, and return some amount of reflected power to the radar system, where special signal processing equipment will determine exactly how far away the object is. This is performed by taking the difference in time between when the incident wave was sent and the reflected wave was received. Additionally, by determining the angle at which the reflected signal was received, an exact point as to where the object is in the sky can be determined. Stealth is able to combat systems like this by optimizing something known as the radar cross-section, or RCS. The RCS is a measure of how detectable an object is by radar. Objects with a large radar cross-section will be easy to detect, while objects with a low radar cross-section will be much, much harder. The RCS is given in units of meters squared. Large commercial airliners like a Boeing 737 or even a Boeing 747 have an RCS as high as 100 square meters. On the other hand, a stealth aircraft like a B-2 stealth bomber is rumored to have an RCS value as low as 1 square centimeter, or roughly the size of a bumblebee. By lowering an aircraft's radar cross-section, you can lower the amount of power reflected to where it is so low that the receive component of the radar system cannot easily detect it, which essentially makes the aircraft invisible. The RCS is mainly composed from three factors. Number one, the material from which the vehicle was made from. Number two, the size of the object, both in terms of the absolute size and the relative size compared to the radar's wavelength. And number three, the angle of incidence from the radar wave and the reflected wave. Starting with the first item, the specific material used to coat the aircraft that is intended to be stealthy is extremely important. Radar absorbent material, or RAM, is material that is specifically designed to absorb the incident radar signals hitting the aircraft. On many stealth aircraft, a specific type of RAM is used called iron ball paint. As radar waves hit the exterior of the plane, oscillations are induced within the coating that alternates the magnetic field of the paint. This causes the radar signals to be converted into heat, which is transferred to the rest of the aircraft and dissipated instead of being reflected back to the source. Secondly, as a general rule of thumb, the larger an object is, the greater the radar cross-section. Large commercial airliners with lots of surface area are able to bounce back a lot of the radar system's power, while much smaller and more nimble jets, such as the F-35, have much less surface area, which immediately lowers its radar cross-section. Lastly, the shape and orientation of the surfaces of an object are extremely important to develop low radar cross-section. As an example, if you notice the F-117 or the B-2 stealth bomber, you will notice that the surfaces are flat and angled in a very intentional manner. This angle causes the reflection from the incident radar wave to reflect away from the source, thus preventing the radar system from ever receiving the signal back for analysis. This, as opposed to a typical commercial airliner, which is rounded in shape and will allow at least some portion of the radar wave to bounce back directly to the source for further analysis. These three principles were exactly what was discovered by Lockheed aircraft engineers in the early 1970s, when members of the Lockheed Skunk Works program found that aircraft designed with certain characteristics could have a very low radar signature. As a proof of concept, the Lockheed engineers built two prototype aircraft that validated the concept, which eventually turned into the F-117 Nighthawk. This became the first modern, purpose-designed stealth aircraft, and although developed in the late 1970s, stayed a complete secret until the late 1980s and early 1990s. Since then, the United States has relied heavily on stealth aircraft, including the B-2 Spirit, the F-22 Raptor, and now the F-35 Lightning, all of which exhibit some form of stealth capability. Other countries are also jumping on the stealth bandwagon, such as China and Russia. In the last decade, China developed the Chengdu J-20 and is also currently working on the more advanced Shenyang FC-31. Russia also has introduced the Sukhoi Su-57, which is expected to be certified for operational use sometime later this year. Stealth technology is continuing to expand its role, and over the last decade, we have seen stealth expand beyond just aircraft and into missiles, helicopters, ships, and now even satellites. This is not to mention the stealth capabilities that are still unknown to the general public and that are in development today. It is rumored that some countries are even experimenting with plasma stealth technology by generating a plasma field around an aircraft as a way to further absorb radar waves. It will certainly be interesting to see where this technology evolves going forward. Leave your comments below on where
Okay, so you have heard, you have heard from another voice what we have already discussed in advance. And so you have seen how the RCS concept has been underlined and how two additional concepts must to three simple cases. In the case we are going to analyze a wavefront which is impacting on a surface in which we do have part of the electromagnetic energy of the wave, which will be absorbed by the materials, increasing its lattice vibration, that is increasing temperature, part which will be reflected, diffracted or refracted, that is scattered, coming back, returning out from the surface, which is the part affecting the value of the radar cross section of our object. And let's suppose to us to illuminate, that's the technical terms, that means to radiate, with a flat wave front, three metal. Now we are going to make an hypothesis just to understand the phenomena, that is three metals materials, three metal surfaces, which can be completely reflective with very simple geometry, a flat plate, a sphere, and a cone. For a plate which is perfectly conductive and which is a flat plate, giving this hypothesis we made, that is, it is completely reflective because it's a metal surface, all the energy which is going to reach the radiated surface will come back and will be returned in the same direction of the incident wave, but obviously with the opposite versus not direction, as it is written, as I wrote here. And so the reflected energy is all confined, restricted in the backscattering direction. And this is, let us say, the most suitable geometrical condition which allow to us to have high detectability of the object. If we move, in the case of a curved surface, for example, the sphere, as we told before, the incident wave is scattered with a certain angle of divergence, and it is not coming back only in the direction of radiation. So not only in the so-called backscattering direction. And due to the interaction that we know of the electromagnetic waves with material surfaces. This situation here, which gives back not all the energy, but just a part of the energy in the backscattering direction, is amplified when we use, for example, a cone, which has also a discontinuity point. That is, here we can think to a very low radius of curvature, because the tip, where the very low radius of curvature is located, it irradiates all over the direction. We can have a quantity which comes back in the backscattering direction, but if we have in mind also, let me say, the rules, because of this angle is the same of the reflected angles, if we have incident beams like this one, where my mouse is on, let me use a pen, this one, for example, you see that in the backscattering direction, which is this one, we do not have any energy coming back, because this angle must be equal to this angle. And so the part of the energy which is reflected is reflected here, not in backscattering direction. And this is explained to us because we do have this, and this was the first experiments, the first solutions, what it was mentioned as F-117, that is F-117 fighters, is the, let me say, the reason because of all that special shape. These models are, in any case, obviously complicated if the wave front does not illuminate the surface in a normal way, but with a certain angular incidence. And so designers must keep in mind that situation like this one, in this case, where the radar cross section due to geometrical factor is very low, if we are going to change the angle of the incidence, for example, this one, okay, the situation could turn towards a situation where the radar cross section is high, and so the object can be considered as detectable. This scattering phenomena, this is just for your purpose. In the case you should in the future, let me say, find something about modeling. We do not have time, and it is also outside my expertise to talk about modeling in this sense, but just to keep to you the concept, are strictly connected, the scattering phenomena we are talking about, to the so-called electrical dimension of the target, which is also called scatterer. They are synonymous. And this electrical dimension of the target or of the scatterer is measured as a function of the wavelength of the radiant source, that is the radar. The wavelength is equal to the speed of the light speed, c, divided by the frequency. So if we, for example, assume a plate having 3 meters on sides, and assuming that this plate is irradiated by a wavelength, here it is called forcing, it's a wavelength, wave of 10 gigahertz, it will show an electrical dimension of 100 lambda, where lambda is the wavelength of the beam, while if it is illuminated, so it is, let me say, radiated with a frequency of 1 megahertz, that is lower than 10 gigahertz, it will show an electrical dimension which is defined as equal to 0.01, the wavelength of the incident beam. And according to this just to let you, let me say, the reference, we can, and we, let me say, define 3 different domains in which the modeling for the scattering phenomena are confined. In the case in which the electrical dimension is higher than the wavelength, this is the domain of high frequencies. And in this case, modeling is based on geometric optics approach, associated with the geometric theory of diffraction as the predominant scattering phenomena. In the case in which the electrical dimension is lower than the wavelength of the beam, this is the domain of low frequencies, which is modeled, which models are based on Rayleigh analysis. Instead, when we do have a resonance, let me say, situation, well, the electrical dimensions are equal to or very near to the value of the wavelength, these the scattering phenomena are modeled by using the so-called analysis of MIA. So these are three different cases in which, when you have to make some calculation and modeling about interaction, as we showed before, you need to refer to the three different tools. Let me conclude today on this. And so we start to enter, having, let me say, made the general picture or the general constraints of this topic. We start to enter to rather absorbing materials. They are mainly complex composite materials, which can be composed by a sort of insulating binder having the role of matrix, and, for example, a magnetic fillers or conductive additives having, for example, dielectric properties, which act, and now we are talking about properties of materials, to reduce the reflected electromagnetic radiation by putting on the table an absorbing phenomena. That is, by absorbing, in addition, I would say, to the positive effect which can be given on the reduction of the radar cross-section by the shape, by absorbing a considerable part of the electromagnetic energy associated to the impinging beam. And this can be done by following two conceptual lines. First of all, not worrying, that is, emitting the signals, but reducing the intensity. And this kind of action is quite suitable for a wide range of frequencies of radars. And these materials that behaves according to this principle, they are also called or known as broadband radar absorbing materials. That is, materials which can give the function of absorbing magnetic energy on a not on only one value of frequency, but on a range of frequency that is on a range of wavelength. And the second possibility is to produce internal reflection, internal to the material, obviously, of the impinging wave, that is of the received signals, that can hinder the reflected signals from the outer surface. And this is essentially made and possible when we deal with only one particular frequency. And materials which belong to this class, they are called, or they are referred as resonant radar absorbing materials, which can have, let me say, interesting application for some commercial, industrial objects, but which are, that's for sure, because they work only with a particular frequency, less suitable, or I would say unsuitable, for the application, the stealth application that we have in mind. Now, having defined this basic concept, we can go on with our more detailed discussion, but this will be done in the next lessons of next Wednesday, before the Easter holidays for all of us. So for today, the lessons concludes. These slides, like also the other ones that we will discuss on next Wednesday, are already on the Google Drive. So if somebody has questions, I'm here to answer to you. Are there any questions? It seems this is not the case, so have a good afternoon and see you on next Wednesday. Arrivederci a tutti.
Arrivederci.
Arrivederci.